All right, we're going to go ahead and do the lab portion of this matching a conditional probability. So here we have this problem where we have got a bag, and that bag has got 4 red starbursts and 2 yellow starbursts. So we're going to be dealing with this bag, but what makes this probability about that is conditional probability is that when you reach your hand into the bag and you choose a starburst, you will not replace the starburst back into the bag before you choose a second starburst. Okay, so that's a big deal. So what that means is the what you get on the next trial or the next pull will have be its probability will have been impacted. So we want to address that issue is what happens whenever the what you get on the second pull from the bag is impacted by what you get on the first. Now, when we play this game, we're going to be considered you will be considered having a winning play if you found a match. So if you picked a red and then the next one you picked was a red and you got 2 reds, it matched and so on and you won. If you had a yellow and you started with a yellow, then and you picked another yellow, that's a match and you won. If you end up with one of each color, you lost. So we're going to walk through what those probabilities are and how likely it is for certain things to happen. Now, do you think, and we'll talk about this, do you think the probability of winning while playing without replacement will be greater than or less than the probability of winning if you put the starburst back in? So let's think about that. If you replaced it, then 4 out of the 6 were red. And so let's say you drew a red. Okay, well, if you're going to replace that starburst back in, what now is your probability of getting red? And so let's say you got a red. So now you still have the same probability. You still have 4 out of 6 are still red in there. Okay, which that's 67% of what's in the bag is still red. But what happens if you pull the first one, it's red, and then you set that aside and you do not replace it? What's the probability of getting another red? Well, what's left in there has only 3 reds out of the 5 in the bag, and 3 out of 5 is 60%. So you have now reduced your chance of getting a red from 67% if you had replaced it to now 60%. So I think if you do not replace it, then it's going to be a lower probability of winning. Okay, so for that second candy, you now have less available, so therefore that's why it's going to be less. All right, so your group is going to play the game 10 times, and based on those results, what's the probability of that winning? So we're going to do experimental results, and then we're eventually going to do theoretically what should happen in the long run. So in order to simulate this game, you're going to go to Today in Canvas. So go to the modules, and you're going to go to today's lesson. So today is Tuesday, and so if you go to the Notes and Lecture Videos page, and you click the Notes and Lectures video page, and you scroll on down, then look there. I have a Desmos link for every class period. So let's click one of those, and it'll probably ask you to sign in. Okay, so I'm already signed in because I had practiced this last night. So here I am, and I had even done this already. So, or you could say somebody had come in here and look, overall results. So this is all the players. So somebody yesterday already played 10 trials. I wonder who that was. But let's play again. So draw a candy, drew the first one, pulled it out of the bag. It was red. Now it stayed out of the bag. Let's draw another one. It was red. Okay, yay. So we won. Okay, let's play again. Draw the first candy. It's red again. Okay, so keep in mind, what's in the bag? 4 are red and 2 are yellow. So it makes sense that I'm getting red more frequently as my first candy drawn. And then there's the second one. Yay, I won again. And so on. Let's play again. Wow, I got red and red. Next, oh, look, here's the next one. I pulled the red, but then I got one of the yellows. Because see, there were only 2 out of the 5 candies in there that were yellow. So there's a 40% chance. So I lost the game. So I want to do this just a whole bunch of times to simulate a whole class period's worth of playing. So we could say, if everybody in the class played, if there were 30 students and everybody played 10 times, then you're going to have over 300 results. But let's see what we got here. I wonder what the answer key, how many draws the answer key had done. Well, say in your group, this is a group that had gotten 4 out of 10. Let's look at my personal results. I had gotten 22 wins and 20 losses. That means I just played this game how many times? With the ones from last night, I have played this game 42 times, and 22 out of the 42 had won. So we could see what that probability was, but it's actually, we know that it's a little more than a half, because 21 would be, so 22 out of 42, so 52% of the time we won in our class. So let's see here. All right. So if we had done it in this case, somebody had done it a whole lot of times, 110 times, and they had won 45 out of the 110. All right. So that is all experimental. That is according to the simulation, or in the going and actually doing the experiment, what actually happened. Now we're going to look at theoretically what would happen in the long run. So I'm going to like this because as we play this game many times throughout the day, we're going to see what we come up with, and then you can see if that's going to be closer to the theoretical. So here we go. So let's try to talk about how this would work, the theoretical. So here we go. On our first draw, we know on the first, the probability, Starburst game, the probability that the first is red, there were 4 out of the 6 that were red, 2 out of the 6 were yellow. So you have now drawn it. And remember, conditional is us not replacing. I took that out and the probability is now changing. So let's just look at the reds. If I got a red, then how many reds are left? 3 out of 5. And there's still 2 out of 5 yellows if I had gotten a yellow. So here's this probability. The probability of getting the first one red and the second one red is this first draw times the second draw, because I do have those independent, those are the probabilities. So I have those events happening. So that's 12 out of 30. So 12 out of 30, we would win. Here, 4 out of 6 and 2 out of 5. So that's how frequently we would lose. Okay. Now, let's do the other half. What happens if the first starburst you draw is a yellow? That's not very like a third of a chance, 2 out of 6. Now, let's say, okay, take that yellow out and put it away. What is left in the bag? Well, I can think what's left in the bag. There's 4 out of 5 are red. 1 out of 5 is yellow. So let's see here. Yep, there we go. 4 out of 5 are red. 1 out of 5 is yellow. So here's getting the first yellow and the second red, 8 out of 30. And then let's do this one. The first yellow and the second yellow is 2 out of 30, so not very likely, but that's a way you could win with yellow, yellow. So I want you to notice these are all the possible ways that you could play this game and get these results. 12 out of 30, you'll win with red, red. 8 out of 30, you'll lose because you'll have red, yellow. And then on this track, 8 out of 30, you'll get yellow and then red, and that's a loss. And then follow this track down here. 2 out of 30 is a yellow, yellow, so that's a win. So if you added 12, 8, 8, and 2, you get all the possible combinations that could happen. That's 30 out of 30. And so that's all the 100% of events that could occur when you draw 2. So let's talk about this situation here. How much total, what is the probability you're going to win? Okay, so to win, you're either going to have red, red or yellow, yellow. So we want to combine, that's the or, those possibilities. So red, red was 12 out of 30. See, look up here at the top. Red, red was 12 out of 30. Yellow, yellow was 2 out of 30. So that's 14 out of 30, which is 0.47. So look at there. That is theoretically, in the long run, if we played this game a whole lot, and so if I came in here and I kept playing this game over and over and over and over and over and over and over again, then it should approach and get closer to that theoretical probability. So I've been keeping on clicking this. And so now let's see, I have 40 wins out of how many total draws? 40 wins out of 67 games. Oh, that's even more though. That's 59%. So interesting. It's not quite matching. Keep going and so on and so forth. So see there, I'm getting some more losses. But if I keep going, you could be higher. You could be lower. That's sampling variability. Okay. And then you get into, oh, well, was that way strange? Does that make me start pulling into question the makeup of this game? Well, here I have 60 wins and 41 losses. That's a total of 101. Oh, wow. Look at that's almost 60% wins. Interesting. So this is very interesting because it seems that it's not quite this theoretical, which should be happening. So it'll be interesting to see as the game goes on today what happens. All right, so now here's the big deal. Here's the main idea for today, besides using this technique of a tree diagram, which, by the way, one major question is, when is using a tree diagram appropriate? Well, that is appropriate if you have these conditional probabilities that change and are impacted. So, for example, if I draw red the first time, so now I'm keeping it out, things are now changing, then there's this probability to win and this probability to lose. Okay? Conditional. Upon drawing red the first time, I have this probability to win and this probability to lose. But if I draw yellow first, then I have this probability to win and this probability to lose. So the probabilities of winning and losing changed based on what you drew first. That's when a tree diagram is going to be helpful. If you have this happen, then it's these probabilities. If you have this happen, then it is these probabilities. That's when you go, whoa, lots of probabilities changing based on what I drew first. If the probabilities are changing based on what you drew first, then the tree diagram is the strategy for you to use. Okay, so now let's look at this. Here's the second big idea. What is the probability that the first candy was red? So we're kind of looking backwards. What's the probability the first candy was red, given that, so if it is known that you have won the game? So we got to predict what was that probability that you you were over here in this first one is red, that you were up here, given that you won. So what we need to do is talk about the total probabilities. So that means I want to just look at all the times I have won. So all the times I have won down here on the bottom was these two ones I start up here. Yellow winning plus red winning. So that's the total amount of times that I have won. On top is this portion of the total that is what I'm looking for. This has to be out of the winning. So it has to be out of these two winning, between these two winnings that are my total winnings, which one of those two had red first. So that's the 1 and red was first. So it's the intersection. It's the intersection of these two things. Out of the 1, you also were red first, and that was 12 of those 30. So that makes it 12 of those 30. And so, wow, look at there, a lot of high probability that, in fact, I'll put that into a decimal or a percentage, 86% chance, 85.7% chance that if you won, it happened because you had drawn red first. Okay? So that is this first idea of this conditional probability. This formula here, the probability of A given B, and you put the totality of the B on the bottom, and on the top is the intersection of the A and the B. So that's the two big main ideas. Now, if you go on to this next one here, then you're going to be working on this. And once again, so I'm going to give you a little bit of time to read this problem. Probability that it's Republican, given that is not continental United States. The totality of, see, look here. In fact, this is what's on the formula chart. The probability of A given that B has happened. So the totality of all the B, in this case, of all the not continental United States. And then on top is what part of that is the criteria I want? What part of the B is the A and B? So what part of the not continental United States is Republican continental United States? All right, so that's what we had here. What part of the winning was the red winning? Okay, so you're going to go through those and work on and then continue with this video. So let's see how you do.
Here we go. So here's another example. Let's do this. I'm going to give you a moment. Go ahead and pause. See if you can't read this situation and then make yourself a tree diagram. By the way, I think the reflection today or tomorrow asks you, when is it that you want to use a tree diagram as a strategy or a technique for your conditional probability? All right. And you want to do that whenever you have a situation where, oh, well, if you're a Republican, then Republican state candidate, then there's this probability for this and this probability for that. But if you are a Democrat, then there's this probability for the continental US and this probability for the non-continental US or whatever. So if the probability is different for one item than the other, you have several different conditional probabilities, several different types of conditional probabilities, then that's when you need to break it down. And that's when you use a tree diagram, when there are several different conditional probabilities. All right, so let me let you take a moment, read through this, and do it. Let's see how your tree diagram comes out. Okay, so hopefully you took some time to do that. We were told here that 3/5 of the time, 30 out of the 50 states went Republican, of the 30 states that went Republican. And then of those 30 states, conditional upon you being one of those 30 Republican states, 29 of them were in the continental United States. So 29 of those 30 were continental US, and 1 out of those 30 was not continental US. Okay? And so then here's those probabilities. All right, next, conditional upon if you are one of the 20 states that went Democrat, that had the Democratic candidate, then here's your results. 19 of those 20 were from the continental United States, and 1 of those 20 were not. Okay, well, be aware that those are different probabilities. You know, this Republican 1/30th of it is smaller amount than the Democratic 1/20th of it. Okay, so that affected these probabilities over here. But when we multiplied it, then of course, 20 times 50 times 1/20th is how we got 1/50th. 20/50th times 19/20th is how we got 19/50th, and so on. All right, so you then multiply those two conditional probabilities together, and here is our total amounts over here. So 29 out of the 50 states were in the continental US of a state that went Republican. Okay, so that's what that looks like. So let's answer some questions. Here we go. First question, what is the probability that a randomly selected state in the US or is continental US and went Republican? Okay, so let me go find that section. Continental US, well, that's these two, this section here, this little wing right here. Continental US is this little section and this little section, but it says continental US and Republican. So then that is just this top little strand. So that's 29 out of 50. All right. Next, we are then asked a conditional probability. We are saying, given that a randomly selected state is not in the continental US. So that is what the denominator is going to be. That's going to say, out of all of the non-continental United States ones. So here we go. Let's look at that. That's this and this. There's the non-continental United States. So out of that, so the denominator is the 1/50th plus the 1/50th. All right, so here's how that looks. So given that it's a non-continental state, then it says what's the probability that it went Republican? Okay, so on the bottom is the total non-continental ones, and the top is the Republican portion of that non-continental. So both of those, that strand, that was those two things, the Republican and non-continental, and that was one of those pieces, that top piece. This 1/50th out of the total 2/50ths. Okay, so from that, we develop that general multiplication formula, which hopefully you can kind of see what is happening. Look here. Here it is. Probability of A given B. All of the B probabilities on the bottom, but the top is the intersection of both A and B. The number one mistake students want to do is they want to just go probability of A over the probability of B. That's wrong. It's not just probability of A on top, it's the intersection of A and B. So let's fix that number one mistake so you don't fall for it. All right, let's do another question. Here we go. Let's see if you can write this out. Given that the randomly selected state is continental. Okay, so that's this. Your straight up and down line is the given that. Given that it's in the continental United States. So we need all of the continental United States ones. Let's go find out what that is. So all of the continental United States, again, was the Republican continental ones, the 29 out of 50, plus the Democrat continental U.S. ones. So we're going to add those to 29 50ths plus 19 50ths. So the denominator should be that, let's see what that is. The 29 plus 19, so 48 over 50. Okay. And then the top part is, what is the Democrat continental U.S. portion? Not all 20, not all 20 out of 50. Not this. That's just probability of A. That's all Democrats. No, it is the Democrat continental portion. That's the 19 out of 50, not the 20 out of 50 is the numerator. Okay? So then that takes us to this. So here we go. That brings us to that 19 out of 40, which was 0.39 something. Okay, try the next one. Given that the randomly selected state is not continental US, what's the probability that it went Democrat? Okay, so take a moment. Let's see how you do on that. First, I write it out mathematically. Given that, straight up and down line, non-continental. And if you remember correctly, that was those 150th plus the 150th. And you know what? The Democrat part was also 150th. So that comes out to be 1/2. All right. So that is the development of that general multiplication rule. So let's see what's happening next. Here it is. And so this works whether we have independent events or not, because see, it's taking into account this conditional upon you being a part B. So given that you are probability B, or you have this event B happening, okay, the total B probability is on the bottom, and the intersection is on top of the A and B. And here it is, the conditional probability rule. Here it is with those symbols. Event A given event B. All right, so now we're going to practice some more of those. But I think the next one has its cards in it. So if you needed to take a moment to study what all's in a deck of cards, here it is real quick. 52 cards, 4 different suits, 13 in each suit. So there are half red, half black. The face cards are the jacks, kings, queens. Okay, let's move on. Here we go. Let me let you look at these and see how you do. What's the probability that the card is a heart given that it is red? So see, I guess I didn't write that out like this. I mean, I could have done this. Probability that it's a heart given that it is red. Okay, so you can do that. So on the bottom is the 26 reds. And on the top is the red hearts. And there are 13 red hearts. All right, try the next one. The card, not the car, but the card is red, given that it is a heart. Okay, so that's interesting. Think about that. What's the probability that it is a red card, given that it's a heart? Well, guess what? There are 13 hearts and 13 red hearts. Okay, so that's 13 out of 13, which is 1. All right, let's see if we can't finish this out. So take a moment, try the others, and then we'll check them. Okay. All right. Here's how C and D came out. Card is an ace, given that it is red. So out of the 26 red, 2 of those red are red aces. This is not 4 on top. That's 4 aces in the whole deck, but we need the 2 red ones, the red aces. Okay, in the bottom, given that it's a face card, there are 12 face cards. We want the queen face cards, and all 4 of the queens are face cards. Okay, moving on. So now, here we go. So this one I found, let's see, what percent. So here we have the biology majors. We're going to take a course in biology research, and I think I'm just going to show you the answers on this one and let you talk it through because my battery on my computer is just about to die. So I think I had even come down here and made a Venn diagram of it to kind of talk through it. Okay. And so I put those in there. So they were all the biology majors. 52 had taken statistics, and then 23 had taken computer, and 7% had taken both. So I made a Venn diagram. Remember, according to yesterday's lesson, you could do a two-way table if you wanted. All right. But take a moment and study through what we have got here. Ineligible, they couldn't take it. Okay. So I'm just going to leave this here and let you take a look at it, and you can look at the notes and study that. And so I'm not going to have time to go through the explanation on that because I'm afraid my computer is about to die. But notice these are not disjoint because you can take, because 7% of students took both statistics and computer. All right. I think then what I'm going to have to do is I'm afraid that I'll just go ahead and finish this video out with a second one going over examples 5 and 6 so that I make sure that I have gotten that taken care of. And so because these will take a little bit of time. So go ahead right now and go through and read example 5 and see if you can make a tree diagram. What happened was when I started reading this, I was like, oh, if the first flight's on time, then there's these conditional probabilities. If the first flight is delayed, then there are these probabilities. So if you have several conditional probabilities, that's when your brain should say, ooh, I should probably organize this as a tree diagram. Several conditional probabilities. So take a moment to finish that example 4 if you did not, and then take a moment to do this tree diagram, and then I'll come back in a second video in the morning to go over that example with you and make sure you have got a strong hold on that.